Greetings and welcome to a new video about analog filter design. In this example we will discuss the Chebyshev response low-pass filter design. We will see clearly the step-by-step calculations for this design, also verifying these in the SPICE simulations. Okay, our design objective is shown here. We need to design a Chebyshev response active low-pass filter. We need to use a Sallen-Key filter circuit configuration and also calculate for our final design the actual stopband attenuation. The specifications for this design for our filter are shown here. We need to have a maximum passband ripple 2 dB, which is given by a max. The minimum attenuation we need at the stopband region is 35 dB. The cutoff frequency we are talking about here is 500 Hz and stopband frequency is 1 kHz. Now at this frequency of stopband frequency 1 kHz, the minimum gain, the attenuation actually, we need 35 dB. That is actually what we need to fulfill. We can go lower. That means, this is of course attenuation, so in the gain it means minus. But you can also go to minus 40 or minus 50 dB. That's all fine, but this is the minimum we need. Let's see how we can design this circuit. Of course, let's see that first step in the calculation step by step. We start first with the filter orders. For that we need to relate this A max and A minimum to the scalars. So that is actually epsilon p, which is then related to that A max using this formula. You substitute here the A max, which is 2 dB, and then you get here 0.7648. Similar for the epsilon s. You substitute here now A minimum of 35 and you get here 56.225. Now taking this together, going to the low pass filter Chebyshev response formula, you see here the epsilon s and epsilon p, which is calculated, and also the stopband frequency and the cutoff frequency from the specification. And that will result in 3.7895 approximately. Now we need to go to the integer values. So in order to fulfill the specifications, we need to go higher. That means we need to go to NS4. If you go for NS3, you will not meet all the specifications in this design. Now the circuit realization for this situation, for this design is interesting because we need to have an NS4, that means fourth order. That means in order to use the Sallen-Key filters, we need to use two-pole Sallen-Key low-pass filters. That is fine, but what is now interesting here, since we talk about the even-ordered Chebyshev response, that's because that is even-ordered, we need to use a gain adjustment circuit also in addition. Otherwise, we will not get the specification at the right location. So the circuit needs actually three parts. Two parts from our low-pass filter, Sallen-Key filter configuration. Those are the two here, two-pole, and the gain adjustment circuit, which is then made by this voltage division RA and RB. So we need to calculate the 10 components here actually in this design. There's 8 for the filter here for the Sallen-Key filter circuit, and also the gain adjustment circuit we have also in addition 2 resistors. So that's step 2, component values. So for this we again, in order to make the design easy, we just select here R1, R2, and R2, R3, R4, everything the same. So just make that R, define it as R, and make that 1 kilo ohm. And then we can calculate the next step, our scaling factor, which is then given by this expression. And now we need to use also the omega c, which is our cutoff frequency in radians per second. That means 2 pi times this fc. Now when you substitute these values here, you get here 3.1831 approximately times 10 to the power minus 7. And this is a very important parameter. We use this in order to calculate the capacitors in this circuit. Now for that we need to use the Chebyshev response 2 dB ripple table. You see here the filter order and all more information. Of course we need to go to the NS4. That is what we require, and we see here indeed what we need 2 sections and also two pole, and these are the parameters for each 2-pole filter circuit. Now, how do we read this? Now for the first part here about the capacitor ratios, that's for the design of a low pass filter. The other row, that's for the resistor ratio, that's for the design of a high pass filter. Now of course we need to go for this, that's what we do. Now we see here the C1 over C, that's for the first 2-pole stage, we need to have a 4.021, and for the second C2 over C, that's actually this capacitor, that needs to be 1.163. In a similar case for the C3 and C4. So how do we do that? Let's go from the table to the actual values. Now first 2-pole, that means C1 is then this 4.021 times the scaling factor C. In a similar form, C2, that is then 1.163 times the scaling factor C. In a similar case, we do that also for the C3 and C4, so we use these two values. Okay, now we have the scaling factors, we have the parameter scale factors from our table, so we can calculate now the 4 capacitors as shown here. So you see here again the scaling factor is appearing and all the calculations are made. Now we have all the capacitors calculated from the selection of our resistors and the scaling factor using this table of the Chebyshev response 2 dB ripple. The final part is the RA and RB for our gain adjustment circuit. So that is what we need to do now. So we need to do the RB over RA plus RB. That is the voltage division, that's the gain actually. That needs to be equal to the minus 2 dB. Now in order to make that, we need to make 10 to the power minus A max over 20. So this is the formula to convert that dBs in a scalar value. So that is actually the following. That means RB over RA plus RB is equal to 10 to the power minus 2 over 20. Now when you do the calculation here, you got approximately 0.79 or approximately 0.8 here. That is what we need to have as a ratio of these two resistors in this form. So we can now make a selection. Of course, this is free to choose, but I make here again 1 kilo ohm as RB. Then we have the following expression. We see here 1000 over RA, which is still unknown, plus 1000 is equal to that same value. Now we can now calculate the RA by using this 1000 over this 0.79, etc. And then we can now subtract this 1000 from the expression, and you get here this resistor final value, which is then 259 ohms. So we have also calculated the resistors RA and RB for our gain adjustment circuit. Okay, let's now collect everything here, C1, C2, C3, C4, and also the gain adjustment resistors RA and RB are here. Now we look at the actual stopband attenuation. That is the calculation we need to make now. Now for the passband frequency, we need to use this formula for the low frequency Chebyshev response. You see here the filter orders, you see the cutoff frequency, and you see also the epsilon P from step 1 here. Now let's substitute everything here. 500, there's 4 for our filter order, and also 0.7648 from here, and that will result in 491 Hertz. Now this is an important frequency, because at that frequency our gain will be minus A max or minus 2 dB. This is actually the connection between this maximum passband ripple and this frequency. We will need to use this frequency in order to calculate also the actual stopband attenuation, because now the formula is appearing. You see here the epsilon P again, you see here the filter order, you see the stopband frequency and the passband frequency. So we need to really have that passband frequency. Now let's now substitute here the values. Again, epsilon P from the first step. Filter order is for 1000 or 1 kilohertz, from the stopband frequency, and this is the 491 hertz from this step. Now when you do the math here, you get here 38.1 dB. This is indeed more than the 35 dB we need to have minimum. So this is indeed according to specifications. Okay, we need to verify our complete calculations and discussion here. So let's go to the simulation result. This is now the Bode plot. You see the gain in blue, that's the curve. The frequency here in the log scale, and also our gain in dBs here in the vertical axis. This is the circuit in the Tina TI SPI simulator. You see all the capacitors, resistors, and the gain adjustment resistors also here. So what do we see? We see at the low frequency that the gain is minus 2 dB. That is, of course, since this gain adjustment circuit is there, so at low frequencies you will have a unity gain feedback, so that's the 1, and there's also 1, so the gain is 1 for each stage here. But you get, of course, an attenuation that will make this gain minus 2 dB. That is actually where we have designed this RA and RB. Now, in addition, you see the cutoff frequency also. So you go down here and then you go to the minus 3.01 dB here. That is just at 500 Hertz. So that's also correct. What we also see is that we have a stopband attenuation. That is actually shown here, which is then at 1 kilohertz. So you see here minus 38.1 dB. That's all according to the specifications here. Now what do we see more? Now we see, of course, also the passband frequency here. That is 491 Hertz. That is also what we have calculated, so that's also correct. We see also the peak. So at this frequency, 188 Hertz, we see a peak, which is actually the 0 dB. And we see again a peak here at this 454 Hertz. And we see a valley, so there's a minimum sort of at 347 Hertz. That is the minus 2 dB. We will calculate in the next slide and show you in zoomed in version how these peaks are calculated and the values are calculated. So we met our specifications looking at the simulation results. Okay, now we will zoom in at the region where we talk about the ripple. Now the frequency scale here is now given in a linear scale just to blow up this ripple region, otherwise it is not really visible. And we see now here that the vertical axis is going from 0 dB up to minus 4 dB, just to zoom in that part. So we see here again the low frequency gain, that is indeed minus 2 dB. Now it's going up, that is actually the ripple. At this frequency, 188 Hertz, we see a peak, which is then 0 dB, and then going down valley at this 347 dB, Hertz I mean. And there's again a maximum at this 454 Hertz. And there's also again a passband frequency, which is actually what we have calculated, 491 Hertz. That's also shown here. That's actually where the ripple stops. And then we see also again the cutoff frequency as we have seen before. How do we calculate now these frequencies? That is now actually done, actually these three frequencies, that's done using these formulas. You see here the peak frequencies and the valley frequency calculations. Now you see how we can do that using the K values. Let's go one by one and clarify this in more detail. If you substitute here, for example, K is 1, this will be, of course, 2 times 1 will be 2 minus 1, again 1. There will be then pi over, and since we have a filter order 4, that means this is 8. So if we get 491 times the cosine of 8 over pi, that pi over 8 I mean, that will then 454 Hertz, which is shown here. That is indeed the peak, that is indeed correct. The next one, we can now go for the K is 2. Now if you go here for K is 2, you will get 4 minus 1 will be 3 pi over 8. And if you go here for K is 2, they will get 2 pi over 8. And that's actually what you show here, what you see here. And that will result in 347 Hertz. And that is indeed the value. So that is actually again the correct formula. The next one is about the peak. Next one, we already talked about the K is 2, as said before, that is then 3 pi over 8. Then you get 188 Hertz, and that is actually shown here. And those are now the 2 peaks and the 1 valley. Alright, this was our example considering the Chebyshev response low-pass filter design. Don't forget to like and share these videos so that we can reach more people for these interesting topics. Thanks for your cooperation and see you next time in another video. Take care.